Hey guys, today we're going to be looking at how to predict relative solubilities of ionic compounds when put in an aqueous solution. We're going to learn the different rules that you need to know, and we're going to be able to predict by the end of this video whether or not an ionic compound will be soluble when dissolved in water. So let's go ahead and get started. Now the first thing to remember is that when something dissolves in water, that doesn't always mean that it dissociates in water. In the last videos, we talked about how covalent compounds like sugar can actually dissolve in water. I can dissolve sugar in water, but that doesn't mean that the molecule itself breaks apart. In some ionic compounds, what's going to happen is you're going to dissolve it in water, and when that happens, it also dissociates. If it does dissociate, we call it soluble. If it does not dissociate, we call it insoluble. Now remember that when ionic compounds dissociate, they break into their ionic components. When they're in their ionic components in an aqueous solution, one property that they have is the ability to conduct electricity. Therefore, we consider them to be electrolytes. The stronger the electrolyte, the more conductive it is. While strong electrolytes are those things that fully dissociate in water. Now, in addition to things being fully soluble, which means they fully dissociate in ions, some things out there are also what we call partially soluble. That means that some formula units or components of it will dissolve, but not all of them. All right, we're going to focus more on the fully soluble or fully insoluble components during this unit, but later on in the year, especially when we get to equilibrium, we're going to talk about how things can be partially soluble, where some things dissociate while others don't. Those things that are only slightly soluble, we consider to be weak electrolytes. Now, these are going to be slightly soluble ionic compounds or weak acids and or bases. Those things that we consider to be insoluble, we would consider to be non-electrolytes, or things that don't conduct any electricity. So we're going to be looking in this unit at different reactions and the potential products of different reactions. So what happens when you create something that is insoluble over the course of a reaction? Well, the answer is that that thing forms a solid, or what we know as in chemistry, a precipitate. And therefore, we call those reactions where a precipitate is formed precipitation reactions. One thing to keep in mind is that this year we focus only on the solubility in water, aqueous solutions. Sometimes you might see the solvent changing to alcohols or oils, and the relative solubilities of the compounds in those things will be different. Relatively speaking, there aren't a whole lot of things that you need to memorize this year. But one of those things that would be extremely helpful to memorize, and to some extent is necessary, are the relative solubility rules of different ionic compounds in water. Below in the description of the video, there's a Quizlet where you can actually test yourself on the relative solubility rules. In addition, on the memorization sheet that I provide, you will be able to see all the different solubility rules that I feel like would be beneficial for you to know. As far as AP Chemistry or the College Board mandates, there are only a couple of solubility rules that you absolutely must know. So let's go ahead and go through the two different solubility rules that you must know. But remember, in my course, I want you knowing more than what the AP mandates. All right? I think it's more functional to be able to have a better understanding of relative solubilities, especially when we get to acids and bases later in the year. The first rule that you have to memorize is that alkali metal salts and ammonium salts are always soluble. Now, a salt is going to be a cation-anion pair of an ionic compound. So if that cation is ever ammonium, NH4+, or an alkali metal, such as sodium or lithium, that compound will always be soluble with zero assumed exceptions. The second rules that you need to understand are that when you're talking about the anions, nitrate, acetate, chlorate, and perchlorate, those compounds also, as salts, are going to be always soluble with no assumed exceptions. Beyond those things that we consider to be always soluble, let's now talk about the things that are almost always soluble. For instance, chloride, bromide, and iodide salts are almost always soluble. The only exceptions to this would be when they're paired as an anion with the cations silver, mercury, or lead. So for instance, lead iodide would be insoluble even though iodide salts, like I said, are regularly soluble. So those are our three exceptions to those relative solubilities. Also, sulfate salts are almost always soluble with the same exceptions. When paired with lead, mercury, or silver, those anion-cation pairs would be considered insoluble. In addition, when sulfate is paired with calcium, strontium, or barium, those would also be considered insoluble. Finally, we're going to look at the ides. So these are going to be the salts that are ending in IDE. Most of these are going to be insoluble, outside of the rules that we've already set. So sulfide salts and hydroxide salts are almost always insoluble. But those obviously come to the exceptions that we've already talked about. For the hydroxides, these are going to be considered bases. The things that are always soluble for our bases, we consider to be our strong bases. There are only 8 of them. So it's the alkali metal hydroxides that we've talked about. But in addition, there are 3 others. Calcium, strontium, and barium hydroxides are all strong as well. We consider those to be fully soluble. All other hydroxide salts are considered insoluble or, at best, weakly soluble. Therefore, they are not strong bases. So let's take a look at a time when this plays into actually real life. Gatorade. Now, if we look at Gatorade, it says it's full of electrolytes. Electrolytes are just ions. So if it's full of ions, well, what ions is it full of? The answer to that is mostly sodium and potassium ions. Gatorade's full of these. Remember, sodium and potassium are both alkali metals. This means they are always fully soluble. We consider them to be relatively non-reactive. In other words, they're not going to react with other ions to form solids. Our bodies use these heavily in both cell signaling and messaging, and as a result, we need to make sure we have high levels of sodium and potassium present. We also tend to lose these ions in sweat, so we need to replace those ions to maintain homeostasis within the body. The other thing we use this often is IVs. IVs are saline solutions. They're not actually pure water. If we tried to put pure water into our bloodstream, due to osmotic pressure, our cells would actually fill to the point of lysis and our cells would burst. So if you ever try to give someone an IV drip with pure H2O, you would actually end up killing them with water toxicity. We don't want that. So we introduce a saline solution for that reason. But the saline solution needs to have ions. It can't precipitate out. So again, we use these always soluble ions in order to make sure that we are replacing the lost fluids with fluids that can be readily absorbed and won't harm your patient. One way that you're going to use this knowledge in terms of solubility rules is when we're predicting the products of chemical reactions. In the next video, we're actually going to look deeper at that in terms of how we can predict the products and the form of those products through the course of a reaction between 2 ionic compounds. But if we're to look at something and see that silver chloride was one of those products, we would now be able to tell you, based off of what we know in terms of solubility rules, that that would be insoluble and a precipitate would form over the course of that reaction. This is because chloride salts, though normally soluble, in the presence of silver ions forming silver chloride, that is one of the exceptions. Therefore, this would be a precipitate in the reaction. All right, time to do some practice problems. I'm going to do the first couple together, and then I'm going to have you guys do the last 5 on your own so we can kind of test what we've learned in this video. Lead 2 sulfate, first thing, let's just go ahead and write the ionic compound's formula because it's good to practice. Lead 2 sulfate. So we know the charge of the lead ion is 2+. Sulfate as an ion is SO4 2-. Therefore, it's going to be PbSO4. Now, sulfate salts are within our normally soluble group, but remember there are exceptions to that rule. Specifically, one of the exceptions is the lead ion. If lead is paired with sulfate, it is insoluble. I'm going to represent that here just with a red X. Also, sometimes you're going to see this represented as an I or IS, or in the course of a chemical equation, you would see this with a little S next to it, suggesting that it's a precipitate or solid. All right, so you might see this, showing that it is insoluble or solid. Let's look at the next one, sodium acetate. Sodium acetate, Na. Then the sodium is +1, acetate's -1. Therefore, it's sodium NaC2H3O2. Now, both of these components, sodium and the acetate ion, are always considered to be soluble. Therefore, this compound as a whole is fully soluble. Now, in a chemical equation, you're going to see this as AQ, suggesting that it forms an aqueous solution. All right, now that you've had a few seconds to work through these, let's go ahead and talk through them together. Again, I'm going to go ahead and write the chemical equations for each one, or the formula for each one, just because it's good practice. Chromium 3 hydroxide. That means the charge on chromium is 3+. Therefore, each hydroxide ion, which is -1, would need to balance that. So you need 3 hydroxide ions. So it's going to be Cr. And then OH3. Now, hydroxide salts, remember, are not going to be considered soluble unless they're one of our 8 strong bases. Chromium hydroxide is not one of our 8 strong bases. Therefore, we would consider this to be insoluble. Remember, we're not going to worry about partial solubility in this unit. We're going to focus on that later when we get to equilibrium. Silver iodide. Iodide salts are going to be I-. Silver is Ag+, so it's just going to be AgI. And with our iodide salts, it's important to know that we have a situation with silver that is an exception to its solubility rules. Therefore, this is insoluble as well. Something to be aware of is normally halide salts are soluble with the exception of fluorine too. Fluorine, F-, is an exception to most halide salt rules. So even though the iodine and the bromine and the chlorine all kind of adhere to the same rules, fluorine does not. That's an important idea. But in this case, again, silver iodide, insoluble. Next one, potassium nitrate, KNO3. Both of these fall within the rules of always soluble, therefore this compound, always soluble. Potassium permanganate, KMnO4. Again, potassium is a part of our always soluble. Even though we don't have a rule about permanganate, it doesn't matter because it's paired with potassium. So this is going to be considered soluble. And finally, here's your challenge question. It might have thrown you for a loop because of the fact that we have silver ammonium lactate. I guarantee you do not know what lactate's ion looks like. The chemical formula for this, just so you're aware, is Ag, NH4, C6H10O6. That's chaos. That's crazy. And there are no rules that we talked, except for the fact that we said it's ammonium lactate. This is a complex ion, so it's actually an ion formed through the combination, in this case, of 3 different ions. But ammonium's one of those. And ammonium salts are always soluble. So this actually would be fully soluble in solution, even though it might not be something that we were already presently cognizant of. Key factors here. Oftentimes, you're going to be given these chaotic, crazy ions. They're really complex looking and sounding, but they adhere to the same rules. If they're paired with any of the things that we know are always soluble, they will be always soluble in those solutions. So that wraps up today's video. Let's do a quick recap. Today we talked about how to predict the relative solubilities of different ionic compounds that may be formed over the course of chemical reactions. In the next video, we're actually going to predict the products of chemical reactions using these solubility rules that we learned today. Make sure you look through the Quizlet and the memorization sheet before you watch the next video to make sure you know these solubility rules. They're going to come up time and time and time again throughout the course of this year. So it's critical that you have full understanding of what things in chemistry are soluble versus what things are not soluble. I'd like to thank Matt Capone and Chris Capone for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.